Welcome to a slow, beginner-friendly lesson on a mini project, made for absolute beginners. Capstone time. Today we pull all of Phase A.8 together into one small working project. We create a SQLite database. We create a users table. We register users by inserting their username, a freshly generated salt, and a salted hash of their password. We write a login function that verifies a password attempt against the stored hash. And we query the table to display what we built. This capstone combines SQLite 3, parameterized queries, hashlib, salts, and file-based persistence into one realistic application. Pull it all together. Here is the scope. A SQLite database stored in a single file on disk. Inside, a users table with columns for id, username, salt, and password hash. A register function that takes a username and password, generates a fresh salt, hashes the password plus salt, and inserts a row. A login function that takes a username and password attempt, looks up the stored salt and hash, rehashes the attempt with the same salt, and compares. Real authentication in miniature. TinyAuth system. Why SQLite for this project? Because it ships with Python, import SQLite 3, no installation, no server. The entire database lives in one file on disk, which is perfect for learning, prototyping, and small CLI tools. And the SQL you write, create table, insert, select, is the same SQL you would write against PostgreSQL or MySQL in production. The skills transfer directly. Built into Python, every skill in this phase lands in one small project. A database. A hash. A login. Real engineering. Everything together. Connect to a SQLite database with SQLite 3.connect. Pass a file name. If the file does not exist, SQLite creates it. The function returns a connection object. From the connection, get a cursor, the object you use to run SQL. After your work, call commit on the connection to save changes, and close to release the file. Always close what you open. For real code you would use A with block to close automatically, but for learning this is the shape. Connect and close. Create the users table with a single execute call. The SQL is called DDL, Data Definition Language. 5 columns, it is an auto-incrementing integer primary key, username is unique text, salt is a blob, raw bytes, password hash as a blob, and a created at timestamp. If not exists keeps the call idempotent, safe to run multiple times. Commit to persist the schema. The table is now ready to receive rows. Define the schema. Critical security rule, use parameterized queries. Never format user input directly into a SQL string. The wrong version on top is vulnerable to SQL injection. A malicious name like "drop table users" can destroy your database. The right version uses a question mark placeholder and passes the value as a tuple. SQLite binds the value safely, treating it strictly as data, never as SQL. Always use placeholders for any value that comes from outside your code. Block injection. Here are the hashing helpers from earlier lessons, packaged for the project. Hash password takes a plain text password, generates a 16-byte salt, derives the hash with pbkdf2_hmac at 100,000 iterations, and returns the salt and the hash. Verify password takes a password attempt, the stored salt, and the stored hash, rederives using the same salt and iterations, and returns whether they match. We will use these in register and log in. From earlier lessons, a users table is the heart of almost every application. Today we build one from scratch. A real users table. Here is the register function. Hash the password to get a salt and a hash. Insert a row with parameterized SQL, 3 placeholders for username, salt, and password hash. Commit to persist. Notice that we register both Alice and Bob with the same password. Because hash password generates a fresh random salt per call, the 2 rows will contain completely different salt and hash values. An attacker reading the table cannot even tell that Alice and Bob chose the same password. Insert with hash. Here is login. Look up the user by username with a parameterized select. Fetch 1 row. If there is no row, the user does not exist, return false. If there is a row, unpack the stored salt and the stored hash, and call verify password on the attempt. The login function returns true for the right password and false for any wrong one. Notice we never store or even handle the plain text password in the database. Verify the attempt. Query the table to see what we built. Select id, username, and created _@, but intentionally not the password hash. You almost never need to display or export password hashes, they exist only for verification at login time. Iterate over fetchAll to print each row. The 2 users we registered show up with their ids and timestamps. This is the data view a real admin dashboard would show, Useful information about the user without ever leaking the secret material. See what we built. Step back and look at the whole system. We create the database and the users table, that is one-time setup. When a new user registers, we hash their password with a fresh salt and store the salt and hash in their row. When a user tries to log in, we look up their stored salt and hash, rehash the attempt with the same salt, and compare. If they match, login succeeds. When we want to see the users, we query the table. 5 small functions working together: connect, create, register, login, query. A complete tiny authentication system. The whole system. When the login succeeds and the data is safe, you have crossed from beginner to engineer. It works. Look at what we just practiced. SQLite 3 end-to-end, connect, execute, commit, close. 3 SQL statements: create table, insert, select. Parameterized queries to block SQL injection. PBKDF2_HMAC for slow salted password hashing. Secrets.token bytes for cryptographic randomness. File I/O, the database is literally just a file on disk. 6 skills from across the phase, all working together in 100 lines of Python. 6 skills, 1 project. Here is the start of the complete script, the 2 hashing helpers. Notice how short they are. 5 lines for hash password, generate a salt, derive the hash, return both. 4 lines for verify password, rederive using the same salt and iterations, compare. Real authentication logic fits in a tweet. The next section wires these into the database. Helpers first, here is the database wiring. Connect to users.db. Create a cursor. Create the users table if it does not already exist, 4 columns. Define register, hash the password to get salt and hash, insert with 3 parameterized placeholders, commit. About 12 lines of real code. The same structure would work against PostgreSQL or MySQL, only the connect call and the parameter style would change. Database wiring. Here is the login function and a demo run. Login looks up the salt and hash for the username, parameterized, fetches 1 row, returns false if the user does not exist, otherwise calls verify password. The star row syntax unpacks the row tuple into the salt and expected arguments. We register Alice, then test 2 login attempts. The correct password returns true. A wrong one returns false. Then we close the connection. Done. A complete working system in under 50 lines. Log in and run. Save the script as register_and_login.py and run it with UV. You should see true then false printed. Then open the database file with the SQLite 3 CLI tool. Tables shows the users table. Selected username from users shows the registered row. That .db file is a real SQLite database you can ship, query from any language, or inspect with any SQLite tool. You built it from scratch. Run it yourself. Or could you take this from here? Swap PBKDF2 for Bcrypt or Argon 2 if you can install a library. The username column already has unique, catch the integrity error and show a friendly message when someone registers a name that exists. Add columns for email, role, and an active flag. Use a context manager so the connection closes automatically even on errors. Add a pepper, a server-wide secret stored in an environment variable, that gets mixed into every hash so a database leak alone still cannot crack passwords. Take it further, look back at the whole phase. You learned to hash strings with SHA-256. You learned to hash files of any size with chunked reading and update. You learned why plain text passwords are catastrophic, what salts do, why slow hashes matter, and how to use PBKDF2_HMAC, Bcrypt, and Argon 2. You met encryption concepts, symmetric, asymmetric, at rest, in transit, cloud KMS. And now you have built a complete tiny authentication system on top of all of it. The whole phase, in one breath. Hashing fingerprints data, encryption hides it. Salts and slow hashes protect passwords when the database leaks. Parameterized SQL blocks injection. A users table that stores salted password hashes, and verifies logins against them, is real engineering you can be proud of. Everything in this phase is what every backend, every cloud service, every application does under the hood. You have crossed from beginner to engineer. Phase A.8 in one breath. Where could you go next? Turn this into a small CRUD app, create, read, update, delete users with proper permissions. Add a click CLI around register and login so you can manage users from the terminal. Move the database to AWS, RDS PostgreSQL, and watch the same SQL work against a managed cloud database. Add HTTP endpoints with Flask or Fast API so other programs can register and log in over the network. The capstone is the foundation. Everything you build from here rests on it. Beyond Phase A, if you want practice, add a third user. Register Charlie with a strong passphrase. Test the correct login and a wrong one. Then write a function count users that returns the number of rows in the users table. You will need select count star from users and fetch on. When that works, you have extended the project yourself. That is how learning sticks. Take the working code and change one thing at a time. Add a third user. Thanks for building the capstone. Phase A.8 complete. Phase A.8 complete.